quadric is something has the equation of the set and has degree 2. So surface we talk about, quadric surfaces, they will have equation of degree 2. Now we look at two special types of surfaces, okay, in the past. Okay, what are the two special types of surfaces that we talk about in the past? We talk about plane, right? What are the general equation for a plane? You can remember? AX plus BY plus CZ plus D equal to 0, right? So you can write it that way. So for planes, the equation will have degree, first degree, right? And then another type of surface will be sphere, we talk about, right? Do you remember the equation for sphere? X minus, you can say A, right? Parentheses square plus Y minus B, parentheses square plus D minus C, parentheses square equal to what? R squared, right? R squared, yeah, got it. Okay, so here. So those are the two types of surfaces we talk about, okay? Now today we're going to investigate two other types of surfaces, cylinder and quadric surfaces, okay? Now, in order to sketch the graph of surface, okay, of a surface, it's useful to determine the curve that intersects the surface with the plane that's parallel to the coordinate plane, okay? And those are called traces, okay, or cross-section of the surface. Okay? So what are the traces? We're going to look at some examples. Remember, you're going to use those planes that is parallel to the coordinate plane to cut it. Okay, so imagine you slice it with those planes that's parallel to the coordinate plane. So let's take an example. Okay, here's one. The first example. This is an example of a cylinder. Okay, so now in the past, you think about cylinder is kind of like this, right? So you think a cylinder looks like this way. But today, we're going to expand the definition of cylinder, okay? We define a cylinder this way. It's a surface that consists of all lines, okay, which called ruling, that are parallel to a given line and pass through a given plane curve, okay? So, so this is a cylinder, but others will also call it cylinder. So for example, I can also have this, and I can write it over here, but I can also have something like this, okay, as a cylinder, okay? I can also have something like, actually, irregular, okay? But it doesn't have to be a circle over here, okay? So those are called cylinders. Now let's graph this. Let's sketch the graph for this surface, okay? D equal to x squared. Any idea how do you do this? How about we look at this well, notice that in this equation, does it mention about the y, the variable y? It doesn't, right? So that means y could be any number. So let me pause a moment and let you guys think about it. So let's use trace to sketch this quadric surface with this equation. Remember to find the trace. Remember, a trace is the intersection of the plane that is parallel to the coordinate plane and intersect with the surface. Okay, so imagine you take for example, look at this one here. Actually, I draw it using the computer. So you're going to take the equal zero. What is the plane? Yeah, it's the xy plane. So you're going to take the xy plane and cut it. Okay, so slice this. And then we want to see what is the intersection curve, right? So we put the equal in this, and find the trace in the xy plane, right? In the xy plane over here is what's in the curve. You can start D equals 0. So this e equal to 0, so that will be on the x margin. And you take this e equal to 0, what kind of equation you get? You get what? X squared plus y squared over 9, and then what? This part over here will become what? 0 equal to 1, right? So x squared plus y squared over 9 equal to 1, that is equation of what kind of conic section? X squared plus, let me write it down. So because b equals 0, then we're going to get x squared plus y squared over 9. And then this part over here, this part here will become 0, right? And then that's equal to what? Which is equal. So this equals to 1. This is reminding you of the equation of what kind of condensation. It is a ellipse, right? Like this is an ellipse. Okay. All right. So it's an ellipse, okay? The standard equation of an ellipse is this one. I wrote it down here. So this is going to be ellipse, okay? Now, in general, the horizontal trace in this plane D equals K. Suppose you substitute here D equal to K, then what kind of equation you get? So now you have what? X squared plus y squared over 9 plus, now we're going to substitute the D here to be K, right? K squared over 4 equal to 1. Okay. Then you can actually isolate this, right? So x squared plus y squared over 9 equal to what? 1 minus k squared over 4, right? Okay. So if you substitute different k, you get the equation like this. Which is what kind of a conic section? What kind of curve? I had something. Did you see ellipse? Right? It's ellipse, right? It's in this form, right? So it's going to be ellipse. Yeah, you got it. So which is an ellipse? Providing that this side here will be positive. So now you're looking at this solid right here, right? So in this, so when you set z equal to different constants, so imagine that you cut this, it's kind of like a football, right? Or an olive, okay? Now let's take this. Let's z equal to different constants. So here's the z-axis. Let's write it. Z equal to 1, right? You get an ellipse, right? Z equal to 2, right? You get an ellipse. Z equal to -1, right? You get an ellipse. So all those traces are ellipse when you set z equal to different constants. Okay. Similarly, if you take the word parallel to the YG plane, right? So parallel to the YG plane, you're going to let x to be a different number, right? So here's the x-axis. So you get this x to be different number, which like it. Okay. And I want to see what kind of trace we get. What do you think? Let's set x equal to different constants. What should I put over here? Replace the x here by k. And then isolate this. 1 minus k squared. Yeah, you got it. Okay. Oops, sorry. Yeah, it's 1 minus k squared. Now replace the y here by k. Let's isolate x squared plus g squared over 4. And what should I put over here? 1 minus k squared over 9. Yeah, you got it. Okay. So that will be this one. Again, they are ellipse, right? So over here, I actually use different color over here. So if you take the vertical plane parallel to the xg plane, you get ellipse. You take the vertical plane that cut this parallel to the YG plane, also get ellipse. So all those traces are ellipse like that. Okay. So in this one, it shows. So it can actually help you to see the shape of the surface. Okay. Now, what do you call this surface here? It is called an ellipsoid, right? Kind of like those pills that you take, right? Ellipsoid, right? So all of traces are ellipses. So it's called an ellipsoid. Okay. Note that it's symmetric with respect to each coordinate plane because the equation involves only even power of x, y, and z. Okay. So this is called ellipsoid. I kind of like this name, ellipsoid. All right. Question? Okay, let's look at the next example. We're going to use the trace to sketch this surface. Okay. First of all, I'm going to ask you, is this a cylinder? It's not a cylinder, right? X, Y, and Z, they're all percent, right? But is it a quadratic surface? Yes. It's an equation of degree 2, right? It's a quadratic surface, okay? But it's not a cylinder, okay? Now let's find out the trace, okay? So we're going to set one of the variable to be 0. So let's set x equals 0. If you set x equal to 0, what does z equal to? Y squared. Yes, very good. So the YG plane is going to intersect the surface in a parabola because this is a parabola, right? Okay. And if you put x equal to another constant, let's say k, you get z equal to what? 4k squared plus y squared. And again, that is a parabola, right? It says z equal to y squared, shifted up 4k squared units, right? Okay, good. That means that if you slice the graph with any plane parallel to the YG plane, because when you set x equal to constant, that will be a plane that's parallel to the YG plane, we obtain a parabola. But what kind of parabola? This parabola here, z equal to this parabola open up or open down? Open up because positive coefficient on the y squared, right? Open up, okay? Okay, now you set x equal to different constant, you find out the trace, right? Similarly, you're going to set y equal to a constant. Okay, so if I set y equal to constant k, and what does z equal to? 4x squared plus k squared. Yeah, you got it. Which again is a parabola that open upwards. Remember when you have this parabola, say quadratic function, you're looking at this coefficient for this, right? When this coefficient is positive, open upward. Coefficient for that negative, it opens downward, the parabola. Okay? Okay, so both this one and this one open upward. Now, we're going to set the variable z equal to a constant, okay? And then you just replace the z here by a constant. And looking at this, what does it represent? What do you think? Ellipse. It has to be ellipse because this coefficient for x squared here is 4 and here is 1. Okay, they don't have the same coefficient, right? So it's an ellipse. Okay, so it's going to be ellipse. Now, after you know the shape of the traces, okay, so you see here it's going to be parabola, okay, and then also parabola like this, and then this will be ellipse. Then you can sketch the surface, okay. And what do you call this surface? Elliptic paraboloid. Okay, elliptic paraboloid. Okay, where does the elliptic come from? Elliptic here comes from, you see this horizontal trace here are ellipse. Okay, and paraboloid. You see this vertical trace here, parabola. Okay, and I think they go by alphabet order, E before P. So it's a elliptic paraboloid. It's a very nice name. Maybe sometimes you can name a baby after elliptic paraboloid. It's a very cute name. Okay. All right. Now, some of you might think, wow, it's difficult, right? Sometimes nowadays, because we have technology, you can actually use the app that I actually referred to, recommended to you last time, and you can actually draw that. Enter this equation, you can see it, okay? So, ellipse, the trace, and then here, parabola, trace over here. So it's called elliptic parabola. Okay, let's look at this example. Let's sketch this surface. Okay. So the trace in the vertical plane, and if you set x equal to k, and then you'll get this equation, which is we recognize it's a parabola, okay? And then it open upward. And then if you set y equal to k, okay, replace the y here by k, you got this. That is a parabola open downward, right? Okay. So if you take the vertical plane x equal to k, so imagine we take the vertical plane x equal to k and cut it, then we end up with parabola. Okay. Now, what about horizontal? Okay. What about if I set d equal to different constants? So when I set d equal to different constant, which means I'm going to take the horizontal plane and cut it with that surface. D equal to different constant. D equal to 0, D equal to 1, D equal to 1, and cut it. Then d equal to k. So we place the d here by k, we get what? Y squared minus x squared equal to k, which is a family of hyperbolas. Yeah, hyperbolas. Okay. So now you see that? Okay. Now putting all this together. Okay. So if you set d equal to k, then you get hyperbolas, right? And then set x equal to k, you get parabola. And then y equal to k, you get also parabola but open down. D equal to k, you get hyperbola. And put all this together, then you get the surface. And that's the surface over here. Okay. It's called a hyperbolic paraboloid. Okay. What is a hyperbolic paraboloid? Okay. Why is it called hyperbolic? Why is it called hyperbolic? Because this, right, the trace here are hyperbolas, right? So the horizontal one. And this way is a parabola open up, and then this way parabola open down. So what does it look like to you? Does it look like saddle, right? Does it look like a saddle? Okay, so it looks like a saddle. Okay. So you see this one, parabola open down, and this way parabola open up. And then if you hold something to side, you have a pair of hyperbolas. Like that. So it's a saddle. Okay. For hyperbolic parabola. Next time people see a shadow, say, oh, that's a hyperbolic parabola. Okay. All right. Okay, this is the next example. Okay, this is the next example. Sketch this surface. Some people will say, oh, we'll just use the app to do it. Yeah. You can do it, but let's try to also understand the trace. Okay, either. So the trace in any horizontal plane d equal to k. So you're going to replace the d here by k, will be this one. Right? Replace z here by k and isolate x squared over 4 plus y squared. You got this, which is what this equation represent what? Ellipse, right? It's an ellipse. Okay. Now the trace in the xz plane, well, in the xz plane, you're going to set what equal to 0. You're going to set y equal to 0. Okay, let's set y equal to 0. So let's set y here equal to 0. You get x squared over 4 minus z squared over 4 equal to 1. Okay, because you set y equal to 0 here. And what kind of curve does it represent? If it's a curve. It's not ellipse. It is what? It is because the minus sign here, it is what? Hyperbola, right? It's a hyperbola. Okay. Now what about the YG plane? For the YG plane, set what equal to 0? Yeah. X equal to 0, right? You set x equal to 0. Then you will get this. Both of them will be hyperbola. Okay. Now how does the surface look like? The surface over here will look like this way. Okay. So it's going to look this way. So this one here is the horizontal plane. Okay. And then if you turn it this way, that will be hyperbola. Okay. And if you put this, the thing that perpendicular to the y-axis, then you also get hyperbola. Okay. Great. Okay. This is called a hyperboloid of one sheet. Okay. So it's one piece. Okay. So we sometimes have hyperbola of two pieces. See the picture. Okay, quadric surface. Okay. I want someone to read this. Okay. Can I have someone to read this paragraph from here to here? Yeah, go ahead.
On such software, the features of the plane x equals k and y equals k are drawn for equal space values of k. As part of the graph are eliminated using including line.
Okay, very good. So when you use those software app or software to graph the surface, they probably have used this method, right? They first draw the trace, and then they will putting all those traces together, then we get the surface. Okay. So this table 1 here shows the graph of 6 basic type of quadric surface in standard form. Let me see if I can make it bigger. Okay, let's see if I make it bigger here. Okay, it's in the note I gave you, right? The first one here is the electron, then that's the equation of this. Notice that it's all times the x here like this. Then this one over here is elliptic parabola, okay? And it will be in this form. And this one here is hyperbolic paraboloid, which is the shadow, okay, will be in this form. This, and this. So, and then this is a hyperbolic of one sheet, okay? And this one is of 2 pieces, this one, okay, between a minus sign. So if you look at the equation, you can actually get them into one of the categories. Okay, by recognizing, looking at the equation, you can recognize what will be the surface. Okay. All right. Notice that this elliptic paraboloid, okay, is going to be like this. Okay. Horizontal traces will be ellipse. Vertical traces are parabola. Okay. The variable raised to the first power indicates the axis of the paraboloid. You see this one? It's to the first degree. Okay. That's the axis of parabola. Okay. You see the axis here? It's the z-axis. So this paraboloid has the axis to be the z-axis. If you replace this by x, and here will be y and z, then you get a paraboloid with the x-axis as the axis, okay, as the symmetric axis. Okay, so this variable of first degree indicates the axis of the parabola. Okay. All right, any question here so far? Now it takes a while to get used to, it's just like meeting new people, new friends, right? This is the first time you see them, and take a while to actually recognize and remember them. Okay, so don't be afraid to do that. Okay, so that's the d-axis. All right, let's take a break and let's come back in. Oh, okay, someone read this from here to here. Then we can take a break. Example
of quadratic surfaces can be found in the world around us. In fact, the world itself is a good example. Although the Earth is commonly modeled as a sphere, the more accurate model is an ellipsoid because the Earth's rotation is caused by magnetic force. Circular paraboloids obtained by rotating the parabola about its axis are used to collect and reflect light, sound, and radio intelligence signals.